And actually, like it's great to be both like talking after Yuri, who gave like a nice interview or like a introduction to what I will follow up on. And I actually presented the work that Yuri like briefly skimmed over 2 years ago at like a conference. Um, and when I was presenting here afterwards, someone came to me and said like, "Ah, we have like a bit of like a similar problem, a similar kind of problem that we're working with." Um, oops. And that is Tito. And this is like a figure from one of his papers where you can definitely see like a sort of like, similar image appear already. And so we decided to actually collaborate on our project. And so I will briefly introduce like the background of what they worked on before going to like the collaboration.
And this is an experiment, right?
Yeah, this is
This
like an experimental.
is not a model. This is a real piece of material.
If you have any questions, please like interrupt me during the presentation. So they did sort of previous work where for a specific type of material, they mainly worked on like metals. If you like pull them in one direction, they see that they get these like what they call like shear bands, right? So like the deformation really localizes sort of between these between the voids, right? It's like sort of the almost like the shortest path that it can find, um, where like all the deformation happens. And if they do like a numerical simulation, they can like plot the values of this like where the deformation happens, and they then can see that it really closely follows like the patterns made by these voids. And so they use this insight to then think um, to say that like, oh, if we didn't know anything about the pattern without doing any simulation, but we just had like a triangulation based purely in the voids, this would encapsulate like almost all of the bands that are happening. And what I then did is like instead of saying we create like a FEM-based simulation based on a mesh, so instead of what we did before was around like every void, we would have like maybe like 100 elements to simulate it with like a finite element model, as we see here. Right, so it would be very expensive, very costly to compute. What if instead we see each one of these triangles as like a single block that is like rigid by itself, but can move like along the boundaries, can like deform along the boundaries. Um, maybe one good thing to mention is that this pattern is only when it has like fully filled, right? So you fully load your material, and then you see like what along which pattern has it like filled or deformed. That is when you get this pattern. And so with this assumption that these are sort of rigid blocks that can move along the boundaries, they like they have two works on this where they can like really efficiently create a sort of an upper bound estimate for what the load is required to make failure happen. This is quite a complicated figure that we don't really need to go into. And the one in the bottom is maybe more interesting, where their theory like produces an upper bound, which is still like quite far above like the true prediction. Right? So this is ideally this would all be like on the diagonal line, but they are like quite far above it. So we talked after like at the conference, and we brainstormed a little bit about like how can we perhaps collaborate in this effort. And we both said we would like to collaborate, but we don't have enough time ourselves to do the work. So there were two master students at Aarhus who did like almost all of the work that I want to be talking about, Rasmus and Tobias. And so the idea was to use a graph neural network on the sort of this triangulation that motivated their work to start. So there were two main objectives. One is we would like to sort of get the pattern that we see here, right? So like where is this deformation happening? And the second one is to care about like how much actual force do we need in total for this to happen, which we call like the total rate of work. So for this, we created like a graph network setup where it was a bit of like a different graph network than I was familiar with, at least, where we had nodes, but we had no node features, right? Because all the information lived at like the edge. What we cared about was predicting a scalar value on the edge. The whole geometry varied between each sample, of course, and also like the features also lived at the edges. So for example, like what's the orientation, how long is an edge, and based on that information, we try to predict like what is the scalar value. Again, it follows like a similar encode, process, decode architecture as before, but now we compute the loss on the edges, like we mentioned before. Yeah, we can go more into detail if you have questions, but otherwise I'm gonna skip over this. So,
Maybe the encoder and decoder, they operate independently across the edges now, right?
just to remove independently, yeah, for each edge there's a separate encoder
Which is
based on the
shared,
features.
right?
It's
Yeah,
shared.
shared.
Yeah.
Yeah. That's right. So yeah, I already jump into like some of the results. So this is like a purely data-driven graph network, which we show like the worst, median, and the best sample from the test set, where I think for the median and the best, you very clearly, I think, see the same pattern occur. And so what we plot here is just like the scalar value. So the graph is of course fixed, and we just predict the scalar value. And it's just that for a lot of them, it is zero, right? And that's why we don't see a link happening there. So this worked quite well in predicting for the specific type of material how the deformation pattern or how this pattern was happening.
And just as a detail, so this is important in practice, because if you got a real piece of material and you loaded it, it would crack, right? So if you loaded a material and it will fracture and crack at some point, and the crack would follow this pattern. And so it's important for us to know like the direction of this crack and so on.
And however, all of these were trained on like the same volume fraction of having these same voids. And so it was all trained on this 21, which performs well. But if we reduce or increase the volume fraction, the performance like decreases a lot. Right? So for here we see that our model predicts almost no shear bands because the things like they're very far away, but there's probably no like link here. And we see that like sort of on average as well, the blue lines should follow the sort of blue background curve. And yeah, same for the other colors as well. And so this didn't really extrapolate well to other geometry spaces. And so where their original model was this like upper bound limit, which was purely like physics based, gave an upper bound. Ours gave a good prediction for the specific value we trained on, but also gave like a pretty didn't give the best prediction when extrapolating. So we're trying like, can we make this better in some way? And that's again where we're gonna put physics sort of more into the model. So the idea was to use an additional so basically use like their theory and not just like completely throw it out of the window, but first run their physics-based simulation, right, which is actually very efficient to run, and use it as like an input to our GNN model. Right, so we give an additional input feature, which is like the output of their limit state analysis. This was very nice in theory. In practice, one thing that made it difficult is sometimes that their the sort of physics-based prior could give the correct overall behavior, but for example, for the just like the like almost the correct location, but just like slightly below it, for example. And in that case, using like a mean squared error would actually make it very difficult. You would have to sort of compensate for the physics-based model being a bit off.
Yeah.
So instead of using the same sort of mean squared error, we changed the loss function to instead focus on like the overall distribution instead of the specific links. So we sort of gave up a bit on like trying to predict the exact shape of the true pattern for gather better predictions on this overall averaged quantities. And now when we use the extrapolation, again, we only train it on 20%, but we see that for where data model didn't predict anything, like any curves, here we do see some curves. Again, the pattern is not correct, right? It's not guaranteed to be correct, but the overall behavior does follow the distribution like quite a bit better. Another sort of benefit was that, and I think I was a bit mixed up, is that the by giving statistics prior, we could learn on a lot less data. Yeah. And yeah, I mean, the previous talk was a bit all about the data requirements already. So this was like sort of an extra nice benefit. But I think the main result was that by training it at only 20%, we could still extrapolate very well to these like lower and higher data regimes. Even though both are only trained on this coefficient of 20. So this sort of results in having two models. One you can train for one specific type of data and predicts very well like the overall specific pattern you want to look at. And then this hybrid model, which gives the average quantities and transfers those much better across different form functions. I think I went quite fast through the presentation. It is like a last slide already. Yeah, this is what I just said. We have these two different models. And this allows them to sort of make these predictions that are better than their sort of upper bound analysis while still being quite accurate. And yeah, there's a couple things that are still would be nice to improve if we could find more people to work on it. But yeah, that's it. Thanks for your attention and let me know if you have any questions.